Hey everyone, welcome to another episode in Physics is Fun. Today is going to be an introduction to circular motion using Newton's laws. Let's jump into reading the question. A roller coaster car has a mass of 500 kilograms and follows the path of the coaster in only up and down motion. A. If the speed at point A is 20 meters per second, what is the force exerted by the track at this point? B. What is the maximum speed at point B, where the coaster is safe and will remain on the track? The radius for point A is 10 meters and the radius for point B is 15 meters. Let's draw the picture for the problem. The coaster has tracks that move up and down like this. Point A is here and point B is here. Let's dot out circles first from point A with a radius r sub A. Also dot out circles for point B with a radius r sub b. With the picture drawn, let's think about the equations for circular motion. For circular motion, the acceleration is centripetal, and so is always center-seeking towards the center of the circle. So centripetal acceleration equals velocity squared divided by the radius. So for the centripetal force, force equals mass times centripetal acceleration. This is all that's really needed for the circular motion, so let's map out the forces for part A with a lovely free body diagram. Part A is asking what force the track exerts on the car, or the normal force at point A. For the FBD of A, start with a base, and the car has a weight straight down, and the normal force from the tracks is straight up. At point A, the centripetal acceleration points up towards the center. This is our direction of motion, and we'll sum the forces for this direction. The sum of forces for points A is normal force of A minus mass times gravity equals mass times centripetal acceleration. Substituting for centripetal acceleration, n sub A minus m times g equals m times v squared over r sub A. Add m times g to both sides, and cancel on the left to get n sub A equals m times v squared over r sub A plus m times g. On the right side, both terms have a mass, so factor 1m out to get m times v squared over r sub A plus g. Now with the sum of forces for part A, it's time to calculate. Rewrite the equation n sub A equals m times v squared over r sub A plus m times g, and now plug in our values of 500 kilograms times 20 meters per second all squared divided by 10 meters plus 9.8 meters per second squared. Simplifying, n sub A equals 500 kilograms times 49.8 meters per second squared, and finally can get 24,900 newtons. The normal force for point A is 24,900 newtons, and with part A solved, let's move on to part B. Part B is asking for the maximum speed, or the max velocity, where the car won't fly off the tracks. We want the car to stay on the tracks, so there should be no acceleration off of the tracks, so the normal force of the tracks must equal 0. I miswrote here centripetal acceleration, but this is how I thought to relate this flying motion with the normal force equaling 0. However, there still is centripetal acceleration on the car. Time to draw a FBD for point B. Starting with a base, the car has weight straight down again, and the normal force of the tracks goes straight up. In this case, the center is down, so its centripetal acceleration is now in the negative direction. So moving on to sum the forces for point B. Normal force of B minus mass times gravity equals mass times negative centripetal acceleration. The normal force needs to be 0, so just cross that force out to get negative m times g equals negative m times v max squared over r sub b. Multiply by negative 1 to make both sides positive, to get m times g equals m times v max squared over r sub b. With the summed forces, it is now time to calculate. Rewrite m times g equals m times v max squared over r sub b. There is a math on both sides, so we can cancel those out to get left with g equals v max squared over r sub b. Multiply both sides by r sub b, and cancel on the right side to get v max squared equals g times r sub b. Now take the square root of both sides to isolate v max, and get square root of r sub b times g. Plug in values to get square root of 9.8 meters per second squared times 15 meters equals the square root of 147 meters squared over second squared, which equals out to 12.124 meters per second. So the max velocity is 12.124 meters per second for a safe coaster where the car won't fly off. We have solved for both A and B, but let's do a little bonus, part C and D. If the track continues and makes a loop like this with a point C, and dot a circle with radius for point C, r sub c, we can explore an interesting concept on roller coaster loops. Part C. If the velocity at point C is 13 meters per second, find the radius needed for centripetal acceleration for point C to equal 2 times gravity. Drawing a FBD as well, weight is again straight down. The cart is on the inside of the tracks, so the normal force the tracks exert is also downwards. So n sub c is straight down, and the centripetal acceleration is also negative and going down towards the center. Now let's calculate. A sub c equals v sub c squared divided by r sub c. Multiply both sides by r sub c, and cancel on the right to get r sub c times a sub c equals v sub c squared. Now divide both sides by a sub c, and cancel on the left side to be left with r sub c equals v sub c squared over a sub c. Plugging in values now, r sub c equals 13.0 meters per second all squared over a sub c, which is 2 times 9.8 meters per second squared. Cancel out 1 meter and second squared to get a final radius of 8.62 meters. So r sub c equals 8.62 meters. Part D. Now find centripetal force for point C if the radius is 20 meters. And is this type of ride even safe? Let's find out and calculate. A sub c equals v squared over r, and plugging in get 13 meters per second all squared divided by 20 meters. This gives an acceleration of only 8.45 meters per second squared. 8.45 meters per second squared is less than gravity at 9.8 meters per second squared. This is not safe. The riders can definitely start to fall out of the car without extra safety nets. These wider circular loops are much more dangerous than the previous teardrop-shaped loop. So, next time you ride a coaster, go for the teardrop to be safe. Or if you're too cool for school, you can be dangerous and go for the large circular loops. After following different points along the coaster, the track exerts 24,900 newtons at point A, and the max speed so the car does not fly off point B is 12.124 meters per second. And finally, for roller coasters to be more safe, they need centripetal acceleration higher than gravity, like the teardrop-shaped loop helps provide. I hope these intro problems are as helpful for you as they are for me. Thanks so much for watching. Hope you come back to learn more exciting material, and see you next time.